Before the break, I was talking about the economic impacts of climate change, and I actually got pretty far, but not quite to the end. So I'm going to do a brief recap, and then we're going to start talking about benefit transfer. Before the break, I hope to get to the social cost of carbon. I forgot my power block, so we may have to take an early break if my computer decides to stop. But we'll see where we are. So before the break, I talked about the impacts of climate change in physical and chemical and biological and physiological terms. And I also talked about just how important adaptation is in all that. And then I said that because these impacts are so diverse, with some small, some large, some positive, some negative, you need to somehow aggregate to say whether climate change is good or bad, big or small. And the indicator that we were going to use is money. And we're using money here as a unit of account. We're not trying to sell anything. And then, I'm still at the recap, so you haven't missed anything. And then I showed you a slightly different version of this graph. A colleague pointed out that there was a mistake here. And said, well, people have used all sorts of methods to estimate these impacts. And the first one was the so-called enumerative method, which is due to Ralph Darch. And essentially what you do is you estimate the impacts in their physical units, and then you find the price for that, you multiply the two and add them up, right? And then most of the time I actually spoke about how to estimate that price for stuff that is not traded on markets, so-called monetary valuation methods. And I said that there's two groups of methods. Some methods use revealed preferences. They look at people's actual travel behavior to find an implicit entry fee to go to the beach or to go to the park. Other methods use purchasing behavior, look at how people buy houses and see whether they are willing to pay more for a house that sits in a beautiful environment. Or look at the labor market, where some people are willing to sell their labor for less if it takes place in a pleasant environment, right? Good thing about revealed preference methods is that they look at actual behavior of real people in real situations. The bad thing about revealed preferences is that you can only use them for direct use values. For everything else, we need to use stated preference methods, where essentially you interview people, you put them in a hypothetical situation and you ask them how much are you willing to pay, or for that matter, how much are you willing to accept in compensation for losing something, right? Willingness to pay to gain something, willingness to accept compensation for losing something. I talked about the difference between the two. And said, well, actually, even though people for a very long time thought that willingness to pay and willingness to accept compensation are the same, almost, they are not in practice. And then we talked about reasons for that. The budget constraint being one, voluntary versus involuntary risk being another, and loss aversion or an adherence to the status quo as another reason why the two may be different, and why typically willingness to accept compensation is greater than willingness to pay for the same good or service, right? And then the final thing I said, that this is relevant for climate because it sort of turns the policy question on its head. In a willingness to pay scenario, we're talking about buying a better climate for our children and grandchildren. Willingness to accept compensation, we're compensating them for imposing a worse climate on them, right? So it's a different policy question. So that is where we ended 2 weeks ago. The one thing that I'd hoped to do but did not succeed is the chapter on benefit transfer. So one thing you should have gotten, should have taken away from what I said 2 weeks ago, is that it's actually difficult to do a valuation study. That there are many pitfalls, there's many things that can go wrong. And because it's so difficult, it's very expensive to do them. A typical revealed preference study would take a decent PhD candidate a year and a half. So you're talking about 30,000, because you also need to pay for travel and data acquisition and stuff. You're talking about 30 to 50,000 pounds. A good contingent valuation study is much more complicated. It would easily cost you 100,000 up to 200,000 pounds. As a result, we don't have complete coverage. One thing I said before the break is that climate change affects all sorts of everything. And that means that you need to know the value of basically everything. Every little piece of nature that can be affected by climate change is essentially what you need to know. And we don't have that coverage, right? What we have is actually a fairly biased sample, a sample that is too small because valuation is so expensive and difficult, but also a very biased sample. So we estimate these impacts, or the value of impact. Typically that's work that is done in the United States, in Canada, in Germany, in the United Kingdom. And that is sort of where it ends. We don't have a lot of primary impact studies in Africa or in Asia or in South America, right? So we need to be able to extrapolate from the things that we have estimated to the things that we're interested in. And also a lot of these estimation studies are done, or these valuation studies are done in different contexts. People have looked at the value of forests in the context of acid rain. But we are interested in the impacts of climate change, not in the interest of acidification, right? So we need to be extrapolating that as well. And then of course, climate change has the additional issue that it's a problem of the future. So we would want to know the monetary values in the year 2050, which of course by definition we cannot observe, right? For another 28 years. So we need to extrapolate from the present and the recent past to the fairly distant future. Now, the methods for the method for doing so is known in the jargon as benefit transfer. And it's just extrapolation from what you know to what you want to know, right? But for historical reasons, people have called this benefit transfer. And the question is, how good are we at this? And the answer may disappoint you, if not surprise you. What you're looking at here is the 57 forests in Denmark. Learned something today, there's 57 forests in Denmark. What they do in Denmark is that every 20 years they do a fairly comprehensive study of recreational values. And you're looking here at the surveys of 1997 and 1977. And this is a travel cost study. So they send somebody to every forest in Denmark and they interview everybody who shows up and ask questions. How did you get here? By train or by bus or by car or by bike? Where did you come from? How long did you travel? How much money did you spend? And then also questions about what is your education? How old are you? What is the company that you travel in? And so on and so forth, right? So it's a fairly comprehensive travel cost study. Now, for those 57 forests, they then estimate the value of the forest per acre. right? That is the value that is derived, and that was done. This value, this survey is done every 20 years. So this was done in 1977, in 1997. It's been done in 2017 as well, but those data are not in this study. And then the question is, can you, based on the 1977 study, predict the values of 1997, 20 years later? And of course, we have the data for 1997, so you can also directly estimate that, right? The black triangles that you're looking at here is the forecast error. So take the 1977 data and see whether you can predict 1997. And some of the forecasts are pretty sound, right? Almost no error. And some of the forecasts are 750% off, right? This is quite dramatically bad, right? So this was done by Marianne Sanderson, and the next thing she did was she cheated. And she cheated in the way that she did not make a pure forecast, but she said, what if I know how the family composition changes? And what if I know how car ownership changes? And what if I know how incomes change over this 20-year period? And I plug in that information. And of course, she knows that in retrospect, but from 1977, of course, you did not know that. If you cheat in that way, the gray squares emerge, and you see that the forecast indeed gets a little bit better. It's nothing to write home about, right? Still, errors can go up to a factor 4.
Is the transfer rate kind of like a counterfactual, like using more of the other information to estimate it?
This is a pure forecast. This can be said, yeah, this is a counterfactual. So this is essentially 1977 values imposed on 1997 income, population, car ownership, and what have you. Now this is an easy problem, right? This is Denmark. It's 20 years. Denmark is the most boringest country in the world, right? Nothing changes, ever, right? You would think. This is an easy one. What we do in climate change is that we value a forest in North Carolina and then project the value, we measure the value of a forest in North Carolina in 2015, and then we derive or extrapolate the value of a forest in Pakistan in 2050, right? That is what you do for climate change impact studies. This is a much easier thing to do. But no, it's not particularly reassuring. This is a similar set of exercises, but now the transfer is over space rather than over time. This is all within the United States. What they did was they looked at the value of sport fishing in a particular lake, and a lake that was 100 miles down the road, and predicted one from the other, and then measure the other and see how right or how wrong are we. For sport fishing, for water quality, for other water-based recreation, for water quality improvement. Why is that twice water quality improvement? That must be a typo. Fishing, whitewater rafting, and so on and so forth. What you see is that some of these studies are respectable, right? 1% error, that's pretty good. Others are way off, right? So this is difficult, right? This is very hard to do. Unfortunately, there is no way around it. So we have to live with this sort of consequences. With this sort of errors, I mean. So, that's all I wanted to say about the impacts or the valuation of impacts, right? So let's return to the methods that we have for estimating the economic impacts of climate change. I talked about the enumerative method. Estimate the things in their natural units, you estimate the price, you multiply the two, and you add them up. And that is all there is, right? There's obvious shortcomings here. This is the most popular method, but there's obvious shortcomings here. One of which is, well, you guys are economists, right? If we see changes in quantities, would we also not want to look at changes in prices? So what you do is you look up, you survey the literature on what does climate change do to the yields, the harvest of wheat, and you see, well, there's a 10% drop in supply of wheat, and then you go to the mercantile, the Chicago Mercantile Exchange, and you look up the price of wheat, and you multiply the two. You would immediately realize that, well, if the supply falls, then maybe the price goes up, right? No, that's not in here, right? So partial equilibrium effects are not in here. Other things that are not in here is you do this separately for every impact. So one thing people have done is estimate the impact of climate change on agriculture, and then estimate the impact of climate change on water resources, and then just add the two up, forgetting that 70% of fresh water is used in agriculture, right? You cannot separate the two, but that is what people have done. So obvious shortcomings, but this is what people have done. The second set of studies uses so-called computable general equilibrium models, where you take the same estimates of the physical impacts, but now you use them to what is in the jargon known as shocking the model. So a change in wheat yields would be interpreted as a reduction in wheat yields would be interpreted as a reduction in the productivity of wheat farms, right? You stick that in the model. It's a general equilibrium model, so it has the partial equilibrium effects. If supply falls, then prices go up. But it's a general equilibrium model, so it has also all the ramifications. So if wheat harvests go down, then the price of wheat goes up. That means that the price of pasta goes up, and that means that consumers switch away from pasta to tortillas, right? And that is included in here. So you see a longer or a more complete set of adaptations in there. And it's not just that you see these things in the output markets, but you also see these things in the input markets. So farmers are confronted with a reduction in their yields, in their harvests, and they may want to hire more people to work the land harder, right? And that means that the demand for labor in agriculture goes up, and necessarily then the supply of labor in other sectors goes down, right? Or farmers may decide to put on more fertilizer on their land, and that of course then means that the demand for fertilizer goes up, the demand for oil goes up, and all those things in the input markets is carried through as well. And then these computable general equilibrium models also model world trade, right? So you also see shifts in production between countries. And if you do this for sea level rise, for instance, you will also see that sea level rise impacts landlocked countries, such as Austria, right? Austria is actually a big winner of sea level rise because everybody else loses land, right? So the countries that are left with their agricultural land intact are actually winners of sea level rise, right? So you see all those things pop up. See the interactions between sectors, obviously. So in that sense, it's far superior. Another thing that is good about computable general equilibrium models is that they come up with a true or a theoretically consistent welfare measure, right? Those enumerative methods essentially estimate the direct cost. And we pretend it's an Higgshian equivalent variation, but it's not, right? So that is the good thing about computable general equilibrium models. The bad thing about these models is that they are based on the national accounts. So things that are in the national accounts are in computable general equilibrium models, and things that are not in the national accounts are not in the models. And there's two key issues here. One is health. So if you feel ill, you go to the pharmacy to buy some medicine, you go to the doctor to get help. Those are economic transactions, right? So if you're ill, you're actually stimulating GDP because you're buying stuff and you hire services, right? The fact that you feel ill and miserable, that is not in the national accounts. What is in the national accounts is your demand for medical services and medical products. So that is in the computable general equilibrium models, not the welfare impact of feeling ill. Another thing that is not in the national accounts is subsistence farming, right? If you grow crops and eat them yourselves, that is not an economic transaction. So that is not in the national accounts and therefore not in the computable general equilibrium models. And those are, of course, the farmers who are most vulnerable to climate change. So those things are omitted from these models. A third method that has been used 3 times is that interview experts. Just ask people what if first select people who you think are experts, and then you interview them. What do you think the economic impacts of climate change would be? I don't see the purpose of this, but this is what people have done repeatedly. And the final method is a bit better grounded, is using statistical methods. And they are typically associated with David Ricardo, who you see here. Now, this often confuses students when I ask in exams about the Ricardian method, and particularly those who did not prepare very well. Ricardo did more than international trade, okay? He was a good economist, a very prolific economist. He lived to a ripe old age. He did many things, right? One of the things that Ricardo did was note that when you buy a piece of agricultural land, a piece of cropland, you do not just buy that land, but you also buy all the sunshine that will fall on that land in the future and all the rain that will fall on that land in the future, right? It's not in the in the contract, but you do implicitly own that, right? And the implication of this is that if you're a farmer and you want to buy some new land, then you would be prepared to pay more for land that sits in a climate that is suitable for the sort of crops that you want to grow, right? That stands to reason. Now, what people have done is estimate this relationship between characteristics of the climate and the value of agricultural land. And this was first done for the United States, and that's a perfectly respectable thing to do, right? How much does climate, rainfall, sunshine, temperature, wind, and all those things, how does that affect the price of agricultural land? It's a perfectly respectable thing to do, and you find a stable econometric relationship. And then you make a jump of faith, and the assumption is that this relationship that you've estimated over space also holds over time. And you project then future climate on this function that you estimated and say, what are the impacts of climate change? And that leap of faith makes two key assumptions. One is trade and the other is technology and institutions. So the trade one is perhaps easiest to understand. So if you look at the Atlantic seaboard of the United States, what you see is that people in Maine grow a lot of wheat, right, because it's cold up there, and people in Florida grow a lot of citrus fruit, oranges and stuff, right? And actually that is much more valuable, right, because this is a niche product rather than a bulk product. So the value of agricultural land in Florida is higher than it is in Maine. So that is what you find. Now, if you then project climate change, a warmer climate on this relationship, essentially what you say, well, the sort of the citrus belt will creep northward, right? From Florida to the Carolinas to Virginia, and maybe in a far future all the way up to Maine, right? That is not how the current distribution of agricultural production works, right? Because it's not the case that people in Maine eat only bread and the people in Florida eat only oranges, right? What you see is that there's trucks going south taking wheat to Florida, and then those trucks turn around, load them up with oranges, and they take those oranges to Maine, right? That explains the current pattern of agricultural production on the Atlantic seaboard. There's a lot of trade going on. And if you now assume that that relationship will also hold over time, then essentially what we're saying is that there will be trucks transporting wheat from 2020 to 2050. It's a bit of a tall assumption, right? And an even taller assumption, you assume that there's trucks from 2050 loaded up with oranges traveling back to 2022. Right? It doesn't work that way. So that is one key assumption that they make. Another assumption that they make is that this relationship that you estimated is stable. That there's no institutional changes going on, that there's no like changes in international trade relations, right? Which is actually one of the main explanatory factors of agricultural production, but also no technological change. Or rather, you assume that technological change is constant over climate space. There's absolutely no reason to assume that. If you look at what is going on in agriculture in particular, the technological change is that it is focused on marginal lands. Most of the technological progress in agriculture is about making bad lands productive. It's not so much about making the best agricultural lands more productive. No, the focus is on bringing more lands into production. So what you see over time is that this relationship flattens rather than steepens or stays constant. So there's things wrong here as well, but this is what people have done, not just for agriculture, but for consumption patterns, for houses, for floods, for all sorts of things. And there's also 2 studies, maybe 3, where they look directly at self-reported happiness and its relationship with climate, right? So those are the methods that have been used. So let's look at the results. And I've shown you a version of this graph before, right? So there are 39 studies with 62 estimates, right? And these numbers are new to me. That's why the hesitation. All the primary studies, -3, are here in the dots and squares and triangles. So those are the primary studies. Recall that on the horizontal axis we have the change in the global mean surface air temperature relative to pre-industrial. So we're already at 1.1 and 1.2 degrees of warming, so this is where we are, right? And then on the vertical axis, we have the Hicksian equivalent variation. So recall that this graph essentially reads as follows. If the world were to warm by 2.5 degrees, then the average person on the planet would feel as if she had lost 1.7% of her income, right? It's not that she's lost 1.7% of her income unless you're Bob Pindyke. It is, you feel as if you have lost 1.7% of your income. So that is how to read the graph. Then the 4 methods that I talked about have different symbols. So the elicitation studies, as you see, are probably the more negative ones. The econometric studies that I talked about before, Ricardo and other econometric methods, are probably the more positive ones. And then the enumerative and the CGE studies are somewhere in between. And then the gray line is sort of a model fit to this. And we won't go into that. The dotted lines is the 70% confidence interval. Right? So this is what we have. And there's all sorts of messages in this graph. The one that people find perhaps most striking is that there seem to be positive impacts of climate change, right? Just earlier this week, the former Prime Minister claimed that the heat wave in early summer meant the end of his stay in number 10. And he was actually ousted because his colleagues were too hot. Now, he obviously saw this as a negative impact of climate change, but there's people who hold a different opinion on this, right? Here you have him. There's other positive impacts of climate change as well. The 3 most important ones are reduced costs of winter heating. If it's warmer in winter, you need to heat your home less and you save substantial money. The second is reduced cold-related mortality and morbidity, which is people being close together during wintertime and infectious diseases running rampant. And the third one I also talked about is CO2 fertilization. That is, CO2 is plant food and makes plants more water efficient. So those are the 3 big positive impacts. But what you see is definitely in the longer term, the negative impacts, infectious diseases, sea level rise, agriculture, biodiversity, and so on and so forth, they actually dominate the picture, right? This very positive impact that you see there, both econometric studies, one is a study that essentially attributes the rapid growth in China to climate change. I think it's a bit of a stretch. The other one is part of the Into Siberia studies by a very prominent economist, published 3 papers in 3 pretty good journals. And there the assumption is free mobility of everything. So climate changes and things go bad in a lot of places, but there's free capital, there's no constraints on the capital market at all. A bit of an iffy assumption, but there's also no constraints on the labor market at all. So essentially what this study says is we're all going to move to Siberia. And in the future, the climate in Siberia will be pretty pleasant, and we'll all be happy and very productive there, right? That is the assumption that is going into this particular study. And you can make of that what you want, but it's been published in a peer-reviewed journal by a prominent economist. So those are the things then are going on. This particular graph is actually, I think, more informative about what this one says, because here you just have results all over the place. And one of the confusing things is that we see things for different degrees of warming. Now, what you can do is use the gray curve to sort of like shift everything to 2.5 degrees, and then just draw a histogram. And if you do that, this particular histogram emerges. And what you see then is that the bulk of the studies actually predicts negative impacts, damages, somewhere between 0 and 2% of income for 2.5 degrees of warming. Now, this is not the stories that you hear in the media, right? This is not the story that Just Stop Oil or Extinction Rebellion wants you to believe. I don't know how closely you follow this news, but just 2 days ago there was this young woman from Just Stop Oil in tears because she thought that climate change would kill her, right? Highly educated woman in England. No, that is not likely. Unfortunately, we are in a situation now where the environmental movement, which claims to be based on science, actually completely ignores the scientific literature and just makes up stuff, right? The projected impact of 2.5 degrees of warming is 0 to 2% of income. Now, to put this in perspective, right? 2.5 degrees of warming, that's 60 to 80 years in the future. This, I mean, 2% of GDP is essentially losing 1 year of economic growth, right? So essentially the central estimate is that 100 years of climate change is about as bad as losing 1 year of economic growth. Right? It's a problem, but it's perhaps not the biggest problem in the world, right? That simply does not follow from what we know about these impacts. So that is an important thing to keep in mind. And yesterday already we talked about how small these numbers were, right? The other thing to keep in mind is that yes, there's a lot of disagreement, right, and a lot of uncertainty about these measures. And I talked about some of the problems in estimating these things. But this uncertainty is not symmetric. That is, the sort of the positive outlier is half the size of the negative outlier. Right, they sort of occur with the same probability, if you want to call it that way, of the same observed frequency in the literature, not in reality. And this is another important thing to keep in mind. That is that negative surprises are much more likely than positive surprises of equal but opposite magnitude, right? And there are three reasons for that. One is just the structure of the science of climate change. That because of all the feedbacks that we talked about in the very first week, the uncertainty about how the climate will change is also asymmetric, so that the best guess of how much the world would warm if the concentration of CO2 in the atmosphere would double is 2.5 degrees. But the range of uncertainties is between 1.5, that is 1 degree cooler than the best guess, and 4.5, that is 2 degrees warmer than the best guess, right? So that uncertainty is already asymmetric. And then all these impact functions are nonlinear or more than linear. And that means that 2 degrees of warming is more than twice as bad as 1 degree of warming, right? So that kicks in, and then you have risk aversion that kicks in, and so on and so forth. And that just means that the negatives are more likely than the positives. And you could also do it more intuitively. You've all heard horror stories about what climate change would do to you, right? You've never probably heard anybody say that climate change will make you very happy, right? And all will be fine. There's hardly anybody who makes that claim, right? There's actually two people who do make that claim. The first one was actually the guy to first talk about climate change, Svante Arrhenius, who thought that climate change was brilliant, right? He lived in Sweden, right? And he thought that a bit of warming could do no harm. The second guy, 70 years later, was Mikhail Budiko, who lived in Siberia. Also thought that climate change could do no harm, right? A little bit of warming can only be good. But those are the two exceptions, right? Other than that, basically everybody will tell you that climate change is bad, and there's a fair amount of people who will say that climate change is very bad, right? Just earlier this week, Guterres, the Secretary General of the United Nations, essentially called climate change a suicide pact, right? Which is completely based on nothing, but that is what sort of the general story that you hear, that climate change is very bad. And some things in climate change can be very bad, right? There are definitely, it's much easier to tell a story about how climate change will make everything go wrong than about how climate change will make everything go right. And my favorite horror story goes something as follows. So if climate changes, if the world warms, then seawaters will expand, sea levels will rise, and low-lying countries are in trouble. And one of the countries that is very low-lying is Bangladesh, right? And Bangladesh is very densely populated, also fairly big, and if sea level were to rise by 50 centimeters, maybe a meter, then 20, 30, 50, maybe 60 million Bangladeshis will have to find a new home. And the question is, where will they go to, right? And at the moment, I mean, they could go into the higher areas of Bangladesh, but that's pretty densely populated as well, and they're not very welcome there. There's a sort of a lot of tension between the people in the highlands of Bangladesh and people in the lowlands. And both culturally and historically, Bangladeshis from the coast who flee somewhere actually prefer to go to India instead. So it would be reasonable to say that if you want to evacuate 50 million Bangladeshis, then a good few of them will end up in India, right? India is not particularly welcoming to refugees. There would be Muslim refugees. India is not particularly friendly to Muslims at the moment. So you can imagine that an influx of 30 million Muslim Bangladeshis into India will cause a lot of problems, right? And may lead to definitely lead to low-level conflict, but you can sort of like see violent conflict break out as well, right? And then the question is, what will Bangladesh do, right? Will it let the Hindus slaughter the Muslim brethren, or will they come to the rescue, right? So you can sort of like paint this scenario from sea level rise to nuclear war on the Indian subcontinent, right? None of the things that I said are outrageous, right? All of these things sort of sound plausible. And those negative impacts, and it's probably going to cost more than 12%, you can tell those stories, right? They are typically not included in here because it's so tenuous, right? The causal chain that I sketched is very tenuous. And one of the assumptions there, I'll talk about sea level rise in Bangladesh a little bit later, but one of the assumptions that I made is that the security situation in 70 or 80 years' time in Bangladesh or in the Indian subcontinent is as it is now, right? Now, if you think back in Europe 80 years ago, or if you think, 80 years ago, right, we were in the middle of World War II. Now Europe is, well, Western Europe, is a very peaceful place, right? 80 years ago, it was outright war. So the assumption that Pakistan and India will still be nuclear armed, probably true in 80 years' time, but will still be sworn enemies in 80 years' time, that does not follow, right? I mean, Germany and France were sworn enemies for a couple of centuries, but are now the best of friends, right? So yeah, you can paint these pictures, but you can also say, well, yeah, it's actually pretty hard to quantify. Therefore, we ignore these stories, but they're much more likely than because of climate change, world peace will break out, right? Putin will go home, Khamenei will resign, and so on and so forth, right? That will not happen because of climate change. So, this is what we know. What are the caveats? I talked about most of them. The one thing I did not say is that the assessment is still incomplete. We're still discovering new things that have not been included and actually turned out to be big. For a long time, tourism was excluded. For a long time, impacts on labor productivity were excluded. At the moment, still nobody has a grip on the impacts of climate change on transport. Is it important? We actually don't know. Do we know? We know it's not in there. We don't know whether this is a big emission or a small emission. Some of these studies omit the interaction between impacts. I talked about that, water resources and agriculture. In the very first lecture on this topic, I talked about adaptation a lot. There's two simple ways of including adaptation. One is to assume that farmers are dumb and they don't adapt at all. That is mathematically very simple assumption. The other simple assumption is to assume that markets are perfect, people are rational, and people are clairvoyant, right? So you see the impacts of climate change coming, there's no barriers to you responding optimally to it. So climate change is not a big deal, right? That is also mathematically easy. The reality, of course, lies somewhere in between the two extremes, but those are the two things that people have included. I talked about nuclear war on the Indian subcontinent. Indirect impacts, I'll talk about next week. So far, we talked about the impacts of climate change on the economy. But if you have an impact of climate change on your economy today, then it will also affect your growth path. It will also affect your future economic production and consumption. And we haven't talked about that. The methods that we use are methods that are suitable for impacts at the margin. So those valuation studies that I talked about is what would happen if one forest disappears or one forest changes a little, right? And then we have a pretty decent idea of what the value, what value people would attach to that. Well, we have not a decent idea, but we have some idea, right? But we are talking about biome changes, right? There's one thing to say, well, we're gonna save 1% of the Brazilian rainforest. How much are you willing to pay for that, right? But we are talking about perhaps 100% of the Brazilian rainforest, right? And your valuation would be different. It would not be 100 times that 1%, right? So we don't quite know what to do with those things. But this is what we have, this is what we know, and this is the knowledge that we should take further. I did decide to skip this particular section, so we're going to talk about social cost of carbon, and then we're going to talk about the distribution of impacts, and we'll continue the implications of, well, maybe not. Let's see how far we get. So far I've been talking about the total economic impacts of climate change, which is very interesting in and of itself. but it's actually not really what informs policy. As soon as you do an optimization, you write down the first order conditions and you're interested in the first partial derivative, right? And that is what governs optimal policy. You can also look at this more informally. If you're in charge of a middle-sized country, say you are elected leader of the Tory party, Rishi Sunak, the most you can hope for is that you'll be prime minister for 2 years, right? So you cannot take away all of climate change in that 2-year period. And definitely if you're prime minister of the UK, you're only in somewhat control of a small share of global emissions, right? What matters for climate change is the global total of emissions accumulated over decades and centuries. So as a single decision maker, you simply cannot take away climate change. The best you can do is take away a little bit of climate change. So we're interested in impacts at the margin, and that is known as the... What was that? What happened? Nothing is connected to this system, right? Anyway, that is known as the marginal damage cost or the social cost of carbon. And essentially what you do, and that's what you need to do for the assignment of next week, unless you've done it already, is you take a scenario of emissions. Along that scenario of emissions, you calculate concentrations of CO2, you calculate climate change, you calculate the impacts of climate change. And then you take another scenario of climate change that differs in emissions in one particular year by a tiny little bit. You again calculate the concentration of climate change itself, the impacts of climate change. You take the difference of these two impacts. Then you have a stream of incremental impacts, and then you discount that back to today, and that is the thing that we call the social cost of carbon. And this is a normative concept in two senses of the word. One, it's normative in that it does not just reflect objective projections of the impacts of climate change, but there's a lot of value adjustments in there, right? We talked about valuation, but there's also the discount rate, and we'll talk about some other things in later lectures. So it's normative in that sense, that this is not an objective measure, but there's a lot of subjective measures. But it's also normative in the sense that it tells us what to do, because this is essentially the Pigou tax, right? This is the external cost, and this is the tax that we should impose on our emissions, right? So, this is a pretty important number. It's called the social cost of carbon for historical reason. I said there were 62 estimates of the total impact of climate change, not 69. I believed it last week, but I don't believe it anymore. The 62 estimates of the total impact of climate change, because it's such an important number. On the 31st of December 2021, 5,397 estimates of the social cost of carbon had been published. Right? Which is a lot of estimates. And you may wonder, like, we have 62 primary estimates, and then we have more than 5,000 estimates of its first partial derivative. That doesn't make sense, right? Because derivatives are just mathematical truisms. The reason that the two numbers differ so much is because the latter is actually easy to do. The first one is hard to do, but also because there's a large number of additional degrees of freedom. So the first thing is that, well, you have those impact estimates that I just showed you. You can fit different curves through those data. And here you see 4 examples of things that have been done in the literature. And that means that if you have a different curve, you have a different derivative right? So that is one reason. The second reason is that you can have different scenarios of warming. So this is the same impact model, but for unabated climate change and for a fairly hefty climate policy scenario, right? And obviously the impacts differ across these scenarios, and therefore the derivative of these curves also differ with the different scenarios, right? People can use different climate models. There's a lot of disagreement there about how exactly to model the climate change, how exactly to approximate all the different processes that are in there. The same is true for the carbon cycle. People have different views on how that thing works today and in the future. One thing we'll talk about extensively is that, there it goes again. I really don't know what is doing this. Those total impacts, of course, come from adding up numbers for different places, adding up numbers across sectors, and how you exactly do that aggregation, people may also disagree about. And then, of course, it's a stream of incremental impact, so we discount it back to today. It's an uncertain future, so we aggregate over a distribution, and so on and so forth. And people may have very different views on how to do that. So that explains why we go from 62 to more than 5,000 62 estimates of the total to more than 5,000 estimates of the social cost of carbon. Now, if you have 5,397 estimates, then of course you can do fancy statistics, right? And the fancy statistics that is shown here is a so-called kernel density. So if we put all those studies together, then this is sort of the histogram or the PDF that results. And what you see is there's a very clear, pronounced middle, right? There's a pronounced central estimate of $70, $80 per ton of carbon. That number doesn't mean a whole lot to you. This is actually roughly equal to the current price of CO2 emission permits in the United Kingdom. So if you believe that this is what the PICU tax should be, we actually got this part of UK climate policy roughly right. I think that happened by accident, but we got it roughly right. You also see that there are some estimates that say, well, actually we should be subsidizing CO2 emissions, as of course some countries still do. There's still lots of subsidies on the use of fossil fuels, but that is a minority of studies, right? And I'll come back to that in week 8, where these negative numbers come from. But actually, the bulk of the estimate says, no, CO2 is bad, we should tax it, right? The further thing that you see is that this right tail is actually pretty pronounced, right? You see that there's a lot of probability mass for higher carbon taxes, much more than for lower carbon taxes. And I cut it off here at 1600, but it actually continues and continues and continues and continues and continues, right? There's one estimate out there that puts the number at, I think it was 100 billion, which I find a bit of an exaggeration, but it continues and continues, right? And again, the uncertainty is asymmetric, right? Negative surprises are much more likely than positive surprises. The thing that is perhaps hard to recognize is these different colors, right? The different colors are different pure rates of time preference. This is the utility discount rate. To find the consumption discount rate, the money discount rate that you're more used to, you should add 2, right? So if you use a 3% pure rate of time preference, you have a 5% consumption discount rate, and essentially you have this PDF here, which is a pronounced PDF. It's actually almost symmetric, and the tail quickly tapers off to 0. Then you can say, well, we should put more weight on the future. We should use a lower discount rate and focus on the purple and the yellow, focus on the purple here in the middle. You actually see a much less pronounced shape, and you see that a lot of the stuff in the tail is actually due to low discount rates. And this is intuitive, right? So if you use a lower discount rate, you care more about the future, and you need to peer further into the future because the future matters to you. If you use a high discount rate, then anything that happens after the year 2100 is irrelevant, right? But if you use a low discount rate, you should actually continue to look further and further into the future. But the further you look into the future, the more uncertain things become, right? And that means that your PDF will lose it will just smear out the further you look into the future. And if you use a lower discount rate, you need to look further into the future, right? So that is the final message from this graph. Now this is the social cost of carbon for emissions in the year 2010. The question then is, what do we do in the year 2011 and in the year 2020, in the year 2030? Because there are so many estimates of the social cost of carbon, there's also 1973 estimates of how the social cost of carbon changes over time. And this is the kernel density for that. And what you see is that the social cost of carbon should increase by 2% per year, right? That is the central estimate. It's fairly symmetric around it with some small wobbles in there, right? So if your social cost of carbon is $100 per ton of carbon, say in the year 2022, then in 2021 it should be 102, in 2022 it should be 104, and so on and so forth, right? That is how this works. Okay. Now let's turn to the distribution of these impacts. So I've shown you this graph, and it's the last time you see it, which tells you what is the impact of climate change on the average person on the planet, which is not an interesting question, right? Because hardly anybody is at the average. Really what you're interested in is a picture like this. How are the impacts of climate change distributed over the world, right? We can draw these maps, obviously. I don't think they're particularly insightful, sorry. I think that a picture like this is much more insightful. So what you're looking at here is the same set of results. This is really the last time. I took the same studies, many of which have also regional detail behind it. And then instead of showing the impacts over time for the world average, I'm showing the impacts over space for 2.5 degrees of warming, right? So it's the same data, same results, but a different cut through the data. So on the vertical axis, we're still looking at the Higgsine equivalent variation. On the horizontal axis, we're now looking at 200 or so countries ranked based on their per capita income in the year 2010. So the poor countries are here, and the richer countries are here. The dots are the central estimates, and then the bars are the 70% confidence interval. And you see a clear pattern, right? Negative impacts, large negative impacts in poor countries, smaller impacts, even positive impacts in rich countries. And the UK actually stands at minus 0.01%. Now this pattern has 3 basic reasons, right? What we see is that poorer countries are much more vulnerable to climate change than are richer countries. And there's 3 basic reasons for this. The first is the structure of the economy. So in the UK, people make money in finance, a little bit of manufacturing, but most workers in the UK are indoors, right? Most actually work in offices. So, what does this? It's no, you're not connected to the system either. Bizarre. So that means that people in the UK economy are simply not really bothered by the weather. We talk about it a lot, but that's because we look out of the window and see what the weather is like, right? If you move to a country like Ghana or other countries in sub-Saharan Africa, then you would see that 50% of income is from agriculture, 70% of the workforce is in agriculture. And that means that they are just more exposed to the weather than people who work in a bank, right? So that is the first reason. It's simply the structure of the economy. The second reason is that poorer countries tend to be in other places than richer countries. Specifically, poorer countries tend to be in hotter places, and richer countries tend to be in colder places. So this is the same data again, but now on the horizontal axis, we're looking at the current average temperature. And what you see is that cold countries benefit from climate change, and hot countries are hit hard, right? And it just so happens that poorer countries tend to be in these hot places. Now, the reason that current heat makes a difference is twofold. One, the plants and animals that we rely on are closer to the biophysical limits in hotter places than they are in colder places. So that is one reason. The second reason is the ease of adaptation. So if you wonder what will Brighton be like in a world that is 3 degrees warmer, the answer is, well, go look at Bordeaux or go look at Marseille. What you see is that people have different buildings there, they have different behavioral patterns, they use different technologies. And if you wonder how should we adapt to 3 degrees of warming, we should become more like the people in Bordeaux, right? That's a fairly simple thing to do. If you live in Singapore or in Jacobabad or in Dar es Salaam, the hottest cities on the planet, you cannot look at how did other people solve this problem of living in a hotter climate, because there are no hotter climates. You have to invent everything from scratch, which is much more difficult than just copying other people's behavior and other people's technology, right? The third reason is that poorer countries have lower adaptive capacity. And that requires some further explanation. What is adaptive capacity? Adaptive capacity is just another term for the ability to adapt, right? And I'm going to talk about adaptive capacity in the context of sea level rise. So if sea level rise, what should you do? Well, one thing you can do is build a dike, right? To keep the water out. So you should be aware of the technological options that you have. And you should be able to build those. And typically in poorer countries have less access to technologies than richer countries do. In this case, that's probably not a big deal, right? I mean, building a dike is a pretty primitive technology. We actually don't know when dikes were invented. We know that the Sumerians, 5,000 years ago, built dikes. So it's a pretty old technology. The ancient Chinese were perfectly capable of doing this as well, right? And you guys probably tried to build a dike or some sort of wall when you were playing on the beach, right? Not very successfully. Did not keep the sea out, but at least you tried, right? And you got the basic concept. So this is the knowledge of how to manage floods is widespread. Of course, the more advanced measures are more costly, right? So the second thing that you need is the ability to pay for this. And here you see a clear difference between rich and poor, right? This sort of stuff costs money. And people who have more can afford to buy more and also buy fancier options, right? One of the things that have emerged in the last 10 years or so in coastal protection are these transparent seawalls, right? Where it used to be that dikes are and seawalls are just made of concrete or made of earth or something like that, and you could not see through them, and a lot of people objected to that. By now we are so good at making glass that you can make transparent seawalls, and you can actually still see the harbor. Those things are very expensive, right? But it is definitely an option for very rich places. The third thing that you need, and essentially coastal protection is a public good, or at least a good that is typically provided by the government, is that you need a government that can raise taxes and then use that money to deliver infrastructure. And you need a government that actually wants to do that. So the government should be able to do those things, but it should also want to do those things. And this is perhaps the hardest to understand, and therefore I'm going to illustrate this with an example. I'm going to look at two countries. Both are deltas, low-lying, very densely populated. Both suffer from floods from the river, floods from the sea, and there's big storms coming through the country. And those two countries are the Netherlands and Bangladesh. And when we talk about the impacts of sea level rise, everybody worries about Bangladesh and everybody looks admiringly at the Netherlands. Right? Geophysically, geographically, they're actually very, very similar. So how do the two countries compare with regard to income? And the Netherlands started serious dike building in the year 1850. So what you're looking at in blue is per capita income estimated in the Netherlands, and it was pretty high for a while, and then Napoleon came along and the economy collapsed, and then it started growing. And in this year, dike building started, serious dike building started. Now if you look at Bangladesh, of course later in time, this is per capita income in Bangladesh. This is Bangladesh that you know about, but this is what is really going on in Bangladesh. They've been growing very, very rapidly, up to the point that in the year 2020, Bangladesh was richer than the Netherlands was in 1850 when it started dike building, right? So in terms of economic resources, Bangladesh is actually better off than the Netherlands was then. Of course, Bangladesh is not better off than the Netherlands is now. If you look at technology, this is not 1850. This is the Afsluitdijk that closed the Zuider Sea. This is 1930. How was this dike built? Well, you see a lot of shovels and men and wheelbarrows, right? You see some drag lines, steam powered. You see a steam train. This is pretty primitive technology, right? 1930. If you look at dike building in Bangladesh, you still see a lot of people because labor is cheap in Bangladesh. But you also see modern drag lines, you see modern materials. So technologically, Bangladesh in 2022 is much better off than the Netherlands was in 1850, right? Much better off. And of course, this picture does not show satellites, computer models, right? All those things, I mean, in 1850, it's essentially engineers worked with abacuses, right? Not with computers. And they used their eyes rather than satellite pictures to survey the situation. So technologically, Bangladesh is much advanced from the Netherlands in 1850, and they're also somewhat richer. Why do we worry about Bangladesh? Well, it is this third component of adaptive capacity, and that is the organization of the government. Bangladesh typically features high on the list of most corrupt countries. So yes, they are able to raise taxes, but instead of using that money for dike building, they're using that money to put in Swiss bank accounts. Right? The money simply disappears. Politics in Bangladesh for a very long time was not so much about doing good for the people, but politicians in Bangladesh have two main priorities. The first is to get rich, and the second is to get even with your political opponent. So that is where most of the activity is concentrated, and then perhaps as an afterthought you want to do something for the country, right? Bangladesh is nominally a democracy, but the poor carry very little weight in decision making because you can essentially bribe them to vote for you, or you can fool them to vote for you. So really it's all about the rich elites rather than about the large masses of people. And there's a good bit of ignorance. There have been surveys. Okay, first I should show this map. So the poor carry very little weight in decision making, but the poor are also the ones that are most vulnerable to floods. So this is a flood map of Bangladesh. So you see floods along the rivers, right? And you see floods along the coast. Now this is a map, the darker the color, the more poor people you find. And lo and behold, the poor people live in the vulnerable places, right? And if the poor don't matter in the national politics, floods don't matter either, right? Because the rich people live high up in the hills. Dhaka is actually relatively high above the river, and many of the Bangladeshi elite live in London, right? Where they're perfectly safe from the floods in Bangladesh. And then there's also a good bit of ignorance going on. If you interview people in Bangladesh, why was there a flood last month? Chances are that the answer is, we sinned and Allah punished us, right? That is why there was a flood. They don't say the government in Dhaka screwed up and did not build a proper dike. No, they blame it on themselves and their God, right? And if you don't make that connection, that it's mismanagement that causes the misery, then of course there is no reason to vote for a party that promises competence in government, right? Now, I hasten to add that this has nothing to do with Islam. When people in the Netherlands were interviewed in 1870 about dike building, some said floods are a punishment from God. And a dike actually gets in the way of that punishment, and therefore dike building is blasphemy, right? So this has nothing to do with Islam. Don't get me wrong. But of course, this is the dominant religion in Bangladesh. Now, what is the difference between Bangladesh and the Netherlands? Well, here's a short history of the country. In 1848, we had the European Spring. People all over Europe rose up, right? Including in the Netherlands, but also in England and in Germany and in France, basically everywhere. In the Netherlands, that led to a new constitution, in 1849, the so-called Thorbecke Constitution, and that did two things. One, it established a strong central government. Until that point, the Netherlands, that's why there is the S in the Netherlands, right? It was a loose federation of fairly autonomous bits. A strong central government that could do things, right? And the second thing is that this government was broadly representative of the people. Until this point, the Netherlands was ruled by what we now call oligarchs. It was ruled by and for the merchant class. Not for the people, but for the merchants, right? And that changed in 1849. I say broadly representative of the population because, of course, women, Catholics were excluded, right? But the Protestant men also suffered from floods. And the first thing the new government did was go after public enemy number one, that is floods, and started building dikes, right? And that is the key difference between the Bangladesh and Netherlands. That in one country you have an able and caring government, and in the other place you do not. 20 minutes left. I can do this chapter. Now, what does this imply for future projections of the impacts of climate change, right? So what I said was that vulnerability to climate change is a function of exposure and adaptive capacity, and both of them change over time, right? If countries grow richer, they change the structure of their economy, they have less in agriculture, become less vulnerable, and countries that get richer also must have a more capable and a less corrupt government, and therefore are better able to deliver those large infrastructure projects that protect against weather and climate, right? So this statement immediately applies the second one, that the future vulnerability to climate change will be very different from the current vulnerability to climate change. Now, how does that work? And I can talk about this in abstract sense, but again, I'm going to just do one example, and I'm going to pick an example that I haven't talked about yet, and that is malaria. What you're looking at here is a map of the world. You recognize that. And what you're looking at is the increase in, or the change, I should say, in the incidence of malaria because of climate change. And there's 4 colors on the map. In yellow, you see increases of malaria of up to 50%. Then in red, you're looking at malaria increases of more than 50%, perhaps more than a doubling in the deep red. In the purple, you're looking at areas where malaria would be introduced, where it is not now. That actually includes the UK. And then in green, there's also green on the map, you see malaria decreasing. Now, why is this? There's 2 reasons for this. So malaria is a parasite, and malaria, the parasite, develops faster when it's warmer. So that is simple, right? Now, malaria also is a complex parasite. It needs to travel through the human body and the mosquito body, and then the human body and the mosquito body. It needs to hop between the two. Now, the mosquitoes that carry malaria are more active when it's warmer, one, and mosquitoes need warm, still standing water to breed. So in a warmer, wetter world, you have more and more active mosquitoes, and you have a parasite that grows faster. That's the disease that develops faster. So in a warm and wetter world, you would expect more malaria. And that is exactly what we see, right? Up to a doubling or more in some places. And of course, in some places, it's predicted to get drier, but by and large, the map is yellow and red, right? So that is one map of the world. The second map of the world is this one. It has 5 colors on. In red, you're looking at where malaria is today, recent past. In yellow, you're looking at where malaria used to be, but isn't anymore. And then in blue and in green and in white, you're looking at those areas where malaria cannot be because it's too cold, too dry, or too cold and too dry. And the question is, of course, what is the difference between the red and the yellow? As I said, yellow is where malaria used to be, but it isn't anymore. Malaria used to be pretty far north. I can't reach that. But there are reported outbreaks of malaria in Stockholm, right? That's what I tried to jump to. George Washington did not want Washington, D.C. to be built on the shores of the Potomac because of the malaria risk. They did not listen to him, right? They built it there anyway, and in the early centuries in D.C. There was a malaria problem. Not anymore, right? So what is the difference between the red and the yellow? Well, if you know your economic geography, you say, well, the yellow parts are rich and the red parts are poor, right? That is something that you should be able to recognize. And that is actually a structural thing. And there's three basic underlying reasons. One is malaria medicine. So if you contract malaria, please don't. It's a nasty disease. But you would go to the doctor and he or she would prescribe some malaria medicines, typically pills, and that has two effects. One, it prevents you falling seriously ill, but it also stops you from being infectious. Now, the parasite needs to jump from human to mosquito to human to mosquito. So if the human is no longer infectious because treated by medicine, then you create, if enough people are treated, you create herd immunity, right? Now, malaria medicine is very cheap. 80 pounds for a course of malaria medicine. And the NHS doesn't think anything of prescribing that sort of medicine to you, right? But in Africa, 80 pounds is a third of annual income, right? It's an enormous sum of money, right? So that is the first reason, malaria medicine. And the second reason is that malaria mosquitoes need small puddles of water to breed. So if you pave your roads, there's fewer potholes. If you put a proper roof on your house and a proper yard around your house, there's fewer puddles of still standing water, right? If you drain your wetlands, there is less malaria habitat. And that is, of course, what we have done. But it's not yet happened in Africa and parts of South Asia, right? And the third reason is clouds and clouds and clouds of DDT. DDT is a pretty nasty pesticide. It was invented, I believe, shortly before World War II. And after World War II, we just sprayed Europe, Italy. We sprayed the southern United States. We moved into Mexico. We moved into parts of Brazil. For a couple of decades, just killed everything in sight, right? Everything that was a small critter. And that got rid of malaria in Europe, North America, and we were doing that, and we were just moving into Africa and just moving into Brazil. And then Rachel Carson wrote Silent Spring in 1962, and we discovered that DDT is bad for birds, and we banned DDT. And that is why that malaria eradication program in South America and in Africa and South Asia stopped. Right? So, poor people, rich people don't die of no malaria, right? Is essentially the moral of this map. And don't believe Rachel Carson. As a side note. Now we're going to project all this into the future. And this was a study that was done in the late 1990s, so 2000 was a forecast. In blue, you're looking at what would happen to the incidence of malaria or the climate change part of malaria if the world would warm, right? And you see that in the year 2000, we believe that around 500,000 people died of malaria in that year. And the model said that 75,000 of those 500,000 was due to climate change, right? So without the warming that we saw in the 20th century, we would have 425 malaria deaths, or 425,000 malaria deaths, rather than 500,000 malaria deaths. So that is what this number means. And then if climate is the only thing that changes, then the number would go up to 250,000 by the end of the century. And then this is the uncertainty about the climate, about the malaria model. Then in green, we add the assumption that it's not just climate that is changing, but also population is growing. And then this number, 1/4 goes to 750,000. 750,000 people dying each year because of climate change, or rather malaria-induced climate change. Climate change-induced malaria, even. And that's a lot of dead people, right? Now, the difference between the two is so large because malaria is concentrated in Africa, and that is where we see most of the population growth, right? In red, we're adding the third component to the scenario. And that is that rich people don't die of no malaria. And if you sort of impose the empirical structure that you see on this map on the scenario, you end up in the red curve. But first the situation gets worse, but then people get rich enough to start affording malaria medicine, and they start paving their yards and building proper roads, and malaria disappears around 2085, right? So in order to project the future impact of climate change, you need to do all these things, right? It's not just climate that is changing, it's population that is growing, it's I'm not happy with this thing at all. It's the economy that is growing as well. But this income elasticity is actually pretty uncertain. The red curve here looks at all countries in the world. If you focus on communist countries only, communist countries tend to spend more on healthcare relative to their income than other countries. You actually see the disease disappear much faster. But then if you focus on public expenditure on health in Africa, you actually see that that's lower than what you would expect relative to their income. And if you impose that particular elasticity, you end up in the purple curve that you see here, where the qualitative pattern is the same. First it gets worse and then it gets better, but it's actually much postponed, right? So that is what we did. And then, this was 1998, we thought of a joke, right? So, you don't recall, this was before you were born, right? Bill Gates stepped down from Microsoft before they had made enough money, and he started the Bill and Melinda Gates Foundation, right? And one of the things that the Gates Foundation said they would do was develop a malaria vaccine. Now, everybody thought he was crazy, because all the experts, basically all the experts said, this is too complex. The disease ecology is too complex to ever come up with a vaccine that works, right? But we, as a joke, said, well, we're going to take Gates at his word, and the stated aim of the Gates Foundation was to have a malaria vaccine in 2020. Second joke, Gates will deliver on time, right? For those of you who know Microsoft and its ability to deliver its products on time, this is hilarious. So, malaria vaccine will be ready in 2020. It took 20 years to roll out the polio vaccine, so that is the time frame that we assume here. And if this malaria vaccine comes along, then boom, the disease is eradicated by 2040. And not just the climate part of malaria, but all of malaria is gone, right? So we did that as a joke. In 2018, 2 years before the deadline, the first malaria vaccine was on the market. Not very good, but now, earlier this year, an effective malaria vaccine is on the market, right? And it is being rolled out. So you need also to take into account developments in medical technology. It also matters, right? So now we have 4 moving parts. But we're not at the end of the story. There was a mule, and I understand that I can make jokes about Asimov again, or references to Asimov again. This is what happened to malaria numbers. So first, the 500,000 that we used in the year 2000 was wrong. It should have been almost 900,000. Malaria mostly occurs in very poor places where they don't properly count the number of deaths, right? Let alone that everybody has a death certificate with a cause of death on. So the actual number was not 500,000 but 800,000. But whereas our model said malaria is on the increase, malaria numbers actually fell. And the reason for this is another mule, that's George Bush. Bush the Younger, the then President of the United States. Now you know Bush as a warmonger, right? This is the guy who was president when the Twin Towers came down. This is the guy who invaded Iraq first and Afghanistan next. You, depending on how left-wing you are, you may think that he's a war criminal, right? That is the popular image of George Bush. Before all this happened, Bush was just a bit of a foolish man, right? Not very right-wing, somewhat right-wing, just a bumbling president. But he is also a fairly serious Christian. And the one thing that he really worked on as a president before 9/11 was the Forgotten Diseases program. So Bush said, I'm going to cure malaria, not through vaccines, because all my experts tells me that is nonsense, but I'm going to put a lot of money into spreading bed nets through the vulnerable areas in Africa to keep the mosquitoes away from the children. And then he also worked to reverse the ban on DDT. And those bed nets are now treated with DDT, so that when the mosquito lands on the bed net, it's not just that it cannot get to the children that are sleeping underneath the bed net, but those mosquitoes actually die when they try to get to the children, right? So that is what he did, right? Put a lot of money into it. And as a result, the number of malaria deaths was falling. And it reversed later on because of war in parts of Africa and so on and so forth. So what do we learn from this? We want to project the impacts of climate change. There are many moving parts, right? It's not just that climate changes, but everything else changes as well. And some of these things change in ways that are unpredictable, right? Actually, this vaccine actually, people said you can't do it, and it happened nonetheless, right? So some humility in forecasts is actually very important. If you ever hear somebody say, well, these are the impacts of climate change with certainty, right? They're either fools or they're lying, right? We cannot really do this with any degree of confidence. Next week, I'm going to draw this to its policy conclusion. We're talking about the Schelling conjecture. And then we're going to talk about climate and growth and climate of development.